Welcome back to Chem 4300. In this video, we're going to continue Chapter 11 on wave mechanics, and now we're going to start talking about uncertainty and commutator relations. Now, in the previous video, we learned about quantum mechanical operators, and something you have to keep in mind is that these operators do not commute. The order in which you apply them will matter, and you will get a different result if you change the order in which you apply them to a wave function. So take, for example, this case. We have two operators, the position operator and the momentum operator. If we apply them with different orders and then take the difference, what kind of result do we get? Now, naively, you might just think, well, that's just going to give me 0, but it turns out that it doesn't. So let's see what this result gives and also what the implications for this are. So if you remember that the momentum operator we worked out when applied to the position basis, it has this form right here. So if we apply to the wave function in the position basis, we're going to apply this difference operator, which we distribute, will look like this. So this means that we're going to apply x first and then p, and then in this case we're going to apply p first and then x, and then take the difference. So in the first case here, that we apply p first, then we're going to have the partial derivative of the wave function with respect to x, then multiply times x, and then you'll have the minus I h bar slide out. Over here, what we're going to be doing is we're going to be multiplying times x first, and then taking the partial derivative with respect to x. And you can see that these are not going to work out to be the same, because you can see this part will just slide over here, but now we have to take the partial of this product. We use the product rule, and we're going to get just I h bar psi minus I h bar x times the partial derivative of the wave function with respect to x. And you can see that this term and this term are going to cancel each other out, and all you're going to have left is that term here, which I can then rewrite down here and show that that difference operator applied to the wave function gives me back the wave function times a number which is not 0. In fact, it's I h bar. So just as I said, like you naively might think that that's going to give you 0, but in quantum mechanics, operators do not commute necessarily, and that means that we can't expect something like this to be 0. In fact, it might actually give you some number here that is non-zero. So this is what we found in that particular case. These type of situations where we're looking at the difference of these, of switching the order of the operators happen so much that actually in quantum mechanics that we give this a name. We call this difference operator the commutator. So the notation we use is that x times p minus p times x is put into square brackets, not curly brackets, not parentheses, but square brackets. And it's going to be x hat, comma, p hat. And in this case, where we evaluated it, we know that the result of that, independent of the wave function, is always going to be I h bar. So this is true for all wave functions that you apply it to. Okay? Now, generally speaking then, we're going to be looking at lots of operators, and when we have two operators that we write down in this notation here, so meaning AB minus BA, if the result of that applied to the wave function doesn't give you 0, then we say that A and B do not commute. Okay? Now, why are these commutation relationships useful? Well, if you remember, for x and p, the momentum and position, we have this uncertainty relationship that the expectation value, the uncertainty in x times the uncertainty in p is greater than or equal to h bar over 2. Well, that actually is contained in this commutator relationship. There's a very general rule in quantum mechanics which says that if your commutator gives you a non-zero value that you can write in this form, I times c, then that will imply that there's an uncertainty between the observable associated with A and the observable associated with B, and that's going to have this form here. So you can see that this commutator here translates to this uncertainty relationship given this general rule here. Now, this is really important because that means that the uncertainty principle that you learn about from Heisenberg's uncertainty principle is more general, and it applies to all operators that correspond to physical quantities that do not commute. There will be some kind of uncertainty principle which you can work out just on the basis of what their commutator gives. Okay? And clearly, if the commutator gives 0, so if A and B commute, and they give a value of 0, that means that you can simultaneously know both the expectation value for A and the expectation value B with infinite precision at the same time. There's no uncertainty relationship like we saw with momentum and position. Okay, so we're going to stop this video here. In the next video, we'll look at the Hamiltonian operator and solving the Schrodinger equation.